10 secret tractor prototypes we almost got. No production schedule, no service manual. There is no public confirmation that they ever existed. And yet, across back lots, military test grounds, and rusting warehouses, traces remain. Prototypes built not for headlines but for problems no commercial machine could solve. Tractors too big to license, too expensive to maintain, or too ahead of their time to explain. Some were designed to float, others were armored, electrified, or powered by twin engines. And while most were scrapped before the first harvest, they still tell a story, not of failure, but of ambition that exceeded reality. This is not a list of tractors for sale. These are machines we almost got and the reasons we didn't. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th. John Deere's bi-turbo 5/8 tractor was too powerful to survive. Before electric engines dominated design boards, there was a time when horsepower itself was the battleground. And some tractors, like this one, were never meant to survive the push. The John Deere 8850 bi-turbo wasn't created to lead a new generation. It was engineered to hold off a threat. Released in 1982, the base 8850 was already formidable, boasting a 15.6-liter V8 diesel engine, four-wheel drive articulation, and nearly 370 horsepower. It was built for the American Midwest, where fields stretch into the horizon and every square mile counts. But when the Big Bud 16 Fi 747 crossed the 900 horsepower mark, and the Steiger Tiger 2 crept past 500, Deere knew their top-end model would need more than just reputation. Their answer wasn't a new frame or transmission. It was pressure, literally. The experimental solution was a bi-turbo system, 2 symmetric turbochargers mounted directly on the existing 955 cubic inch block. If it worked, they could break the 500 horsepower ceiling without redesigning a single gear housing. It was fast, cheap, familiar with their technicians. On paper, it was perfect. But engineering lives in the field, not on paper. From the earliest tests, the prototype revealed 3 critical flaws. The first was heat. Despite the upgraded intercooling, the water jacket around the cylinder heads was unable to disperse the thermal load under boost. Exhaust temperatures climbed to 1,250 degrees Fahrenheit, well beyond the thermal stress limits of the casting alloys used in the 1980s. The second issue was dynamic imbalance. Without a central governor, the twin turbos produced uneven boost pressure, causing rotational discrepancies across the crankshaft. A condition Deere engineers labeled lag shift threatened long-term structural integrity. And the third, perhaps the most damning, was torque overload. The quad-range transmission, originally rated for sub-400 horsepower, failed under bi-turbo torque. Field trials showed deformation on the intermediate shaft after just 32 hours of operation. None of these problems was a surprise to Deere's internal engineering team. However, success would have meant setting a new benchmark for high-efficiency tractors without compromising the company's modular supply chain. If the project were successful, they could ship over 500 HP to North Dakota, mainly utilizing existing infrastructure. So they kept testing. Quietly, no public images were released, no patent filings mentioned the bi-turbo variant, but retired engineers from Waterloo, Iowa, later confirmed its existence. One hand-drawn intercooler diagram appeared on a tractor enthusiast forum in 2007. It was never removed or verified. When the program was shut down, the prototype was disassembled. The engine block was returned to the metallurgy lab for fracture analysis. The final report stated, fracture initiated at cylinder 5, exhaust side, after 41 hours under load. That's all. No headlines, no public failure, no recognition that Deere had tried to cross a line that materials science wasn't ready for. And since that day, no John Deere 5/8 engine has ever approached 500 horsepower again. Ranked 9th, Ursus C360 Hybrid. When Cold War farming met desperation, what happens when you don't have enough fuel to finish the harvest? In the early 1980s, Poland wasn't a hypothetical question. As petroleum shipments across the Eastern Bloc tightened, state planners began looking for ways to stretch every liter of diesel. The Ursus C360, already the workhorse of socialist agriculture, was chosen for a radical experiment. convert it into a low-power hybrid using domestic components, civilian-grade electrics, and whatever was available behind the Iron Curtain. The result was a prototype quietly deployed to collective farms under field trial designation only. The standard four-cylinder diesel was replaced with a smaller unit, just over 35 horsepower, and linked to a fixed PTO generator. That generator fed into an improvised battery bank made from industrial lead-acid cells. A secondary electric motor mounted in line with the drive shaft added temporary power support under load. It was never about innovation. It was about survival. Cold starts and -20 winters had frozen hundreds of engines the year before. This system could pre-warm the block or idle electrically overnight. In theory, it could also offset fuel usage by blending electric assist during short-distance hauling. But theory never matched the realities of rural Poland. The batteries, recycled from train systems and communication bunkers, were dangerously heavy and discharged unevenly. The alternator's output dropped sharply when engine RPMs fell below 1,200, which meant idling wasn't viable in real-world use. Voltage instability caused relay failures after just 40 hours in the field. And unlike tractors in the West, there was no integrated control system. Every switch, every motor, every bypass had to be manually toggled. In one field test outside Lublin, the tractor shut down mid-plow when auxiliary battery output dropped below 9 volts, causing power inversion back into the diesel starter loop. After a short investigation, the hybrid trial was quietly withdrawn. The diesel-only model resumed its role, unmodified, and the electric modules were stripped and resold as standalone generators. No photos remain. No official technical drawings have surfaced. Only a fragment of a service bulletin remains, typewritten in Polish, dated March 1985, recommending against integrated electromechanical retrofit in field units due to thermal discharge risks. And that was the end of one of the only Cold War tractor hybrids never meant for the public. It wasn't about saving the environment. It was about finding one more way to plow a field when the fuel never came. Ranked 8th, Allis-Chalmers fuel cell tractor. Can you call it a tractor if it never pulled anything? In 1959, the Allis-Chalmers Manufacturing Company unveiled something that resembled a farm machine, but was in truth a symbol, not built for work and not intended for fields. Designed instead to prove that electricity could power the American future, without gasoline, without oil, and without combustion. The Allis-Chalmers fuel cell tractor was the first of its kind, an open-frame platform powered by 1,000 phosphoric acid fuel cells, stacked in banks, linked to a low RPM electric motor, and mounted on a skeleton chassis that mimicked a small garden tractor. Its total output was modest, roughly 15 horsepower, and its torque curve was shallow. But none of that mattered, because this wasn't a machine built to till soil, it was a message. At the height of Cold War innovation, just 2 years after the Soviets launched Sputnik and 1 year before Kennedy's campaign to reach the moon, Allis-Chalmers engineers proposed something radical, that hydrogen, passed through a membrane, could split into ions and electrons, making it the heart of a working vehicle. It didn't need a carburetor. It didn't emit smoke. It didn't vibrate. The tractor could idle silently, charge from fixed tanks, and move at a crawl across exhibition halls while engineers explained the science to reporters. It was paraded at trade shows, state fairs, and energy conferences. It was photographed, televised, and studied by university labs. However, it was never used for plowing and never sent to a field. It had no transmission, no PTO, no weight distribution system. The electric motor could move the wheels, but not much else. On one demonstration run, it stalled on a slight incline, unable to maintain consistent current flow from the hydrogen cell stack. But again, performance was irrelevant. Because this wasn't an attempt at commercialization, it was a proof of concept, built to capture imagination, to signal that agriculture might someday leave fossil fuels behind. The prototype was never replicated, no production version was drawn, and after a few years in storage, it was retired to a quiet corner of the Smithsonian. Today, the Allis-Chalmers fuel cell tractor sits under glass at the National Museum of American History. Not as a failed machine, but as the first time someone tried to electrify the land, not with wires, but with a dream in metal. It remains the only tractor in history whose engine compartment was filled with silence. Ranked 7th, Deere X9 military variant. There is no civilian reason to arm a combine harvester. Yet sometime between 2018 and 2021, someone did. They started with the John Deere X9, a high-capacity 700 horsepower harvesting platform, and removed almost everything that made it a commercial product. The green paint was gone. Similarly, the cab comfort package, infotainment console, and glossy dealer branding were also included. In their place, matte panels, composite shielding, blackout lighting, and military-grade filtration systems. The result wasn't a piece of farm equipment. It was an operational asset for contested zones where agriculture, logistics, and security overlap. Reports of its existence first surfaced through grainy off-angle images posted on contractor forums. The machine shown had track assemblies instead of tires, no visible yield monitor, and no front header. Just a reinforced shell mounted over a Deere chassis. No serial number. No VIN. Just the unmistakable outline of a Class 10 combine that had been built for something other than farming. The platform was likely a one-off or limited-run prototype developed either for internal defense testing or as part of a subcontracted logistics program. Its role, secure field extraction of critical grain stores in areas considered unstable or hostile, possibly under government contract or private military operation. Multiple technical modifications were rumored. Cab armor plating is sufficient to repel shrapnel or small arms fire. A filtered air system that may have included nuclear, biological chemical sealing, adapted from civilian hazmat units. Modular wheel sets replaced with tank-style track systems capable of traversing bombed infrastructure or collapsed irrigation berms. The internal grain system was redesigned for faster offload to armored trailers. Operator access was limited. Everything about it was functional. Stripped, silent, and built for redundancy. The location of the X9 military variant's operation is unknown. Some speculated Iraq or northern Syria. Others pointed to North Africa, where food infrastructure has been increasingly targeted. One blurred satellite image from 2020 shows a large self-propelled vehicle matching its dimensions near a UN logistics checkpoint, though identification remains inconclusive. Deere has never confirmed the existence of a military program based on the X9. No public documents name it. No museum holds it. Its origin, use, and retirement remain unverified. But to those who saw it, briefly and usually from a distance, it was unmistakably real. A harvester re-engineered to do one thing: keep moving in environments where standard combines wouldn't last a minute. Ranked 6th, Case Wire H500 Quadtrac semi-autonomous. No steering wheel, no operator, no cabin. In 2017, Case IH engineers rolled a modified Steiger 500 Quadtrac onto a test field in Saskatchewan with one goal: to prove that a 500 horsepower track tractor could run itself. Not in theory, not on stage, but on soil. It wasn't the company's first autonomous concept. That came a year earlier, in 2016, when Case unveiled its driverless concept vehicle at a significant trade show. However, that version was clean, polished, and impractical. A cableless design with no manual operation capability in the event of system failure. Farmers called it a showroom fantasy, so the team pivoted. They took one of their most proven field platforms, the Steiger 500 Quadtrac, and fitted it with a comprehensive suite of navigation systems: real-time kinematic GPS, short-range radar, LiDAR depth sensors, terrain modeling software, and an integrated operations tablet mounted to a streamlined operator station. The result was a semi-autonomous tractor that could start, steer, reverse, and execute predefined field patterns, with no one in the seat. And for a time, it worked. The unit completed multiple harvest passes without intervention. It turned at the row ends. It tracked consistent depth. But problems surfaced quickly. In dry, dusty conditions, the LiDAR lens required constant cleaning. In rain or morning fog, the terrain scanner misread slope gradients. RTK signal drops caused momentary drift, enough to damage the irrigation pipe or misalign the subsoil tillage. There were legal problems too. U.S. federal law prohibited autonomous tractors from crossing public roadways without a licensed operator, even if the machine had full override capability. Insurance underwriters refused to cover uncrewed operations outside of fenced test zones. For farmers managing multiple machines, the remote control system proved too slow to monitor when several tractors were active simultaneously. The semi-autonomous Quadtrac had no fatal flaw, no crash, no dramatic failure. It simply became too expensive to justify. The sensor arrays doubled the cost of the base machine. Service intervals dropped by 30% due to wear on environmental seals. Insects clogged the cooling fans for the radar unit. Backup systems drew too much power for an off-grid environment, and when it broke down, which it inevitably did, no one in the field could repair a vision processor designed in Europe with a 4-week parts lead time. By 2019, most of the test units were either retired, stripped for parts, or converted back into conventional Steiger 500. Case never announced a cancellation. They stopped mentioning it. Today, there are no photos of the semi-autonomous Quadtrac on the company's official website. Only archived press kits and blurred test images remain. Ultimately, the machine performed as intended. It just couldn't do it reliably. And that made all the difference between a prototype and a product. Ranked 5th. Kirovets K9000 Swamp Hauler. It was taller than most tractors, wider than most tanks, and light enough to float. The Kirovets K9000 Swamp Hauler wasn't built for fields or roads. It was engineered to survive Russia's last undeveloped frontier, the peat bogs, frozen deltas, and semi-submerged farmland of the far north. Based loosely on the K9000 chassis produced at the St. Petersburg tractor plant, this prototype was heavily modified to operate where no European import could survive. Its tires were low-pressure, flotation grade, over 2 meters in diameter. The engine was a Mercedes-Benz OM460LA, a 500 horsepower block retrofitted with a sealed air intake, raised to the height of a man's shoulders. It had no standard exhaust stack. The heat cycle was rerouted and contained. Cooling ran in a closed-loop system. The axles were reinforced. The fuel tanks were shrouded, and every ounce of steel below the midline was coated to resist anaerobic mud. It wasn't beautiful. It wasn't comfortable. But it worked. Tested in the swamp regions near Arkhangelsk and later in parts of Yakutia, the machine reportedly operated for 32 consecutive days without being pulled out. No crane, no towing, no track repair. For a country trying to convert thousands of hectares of wetland into arable soybean zones, it seemed like the perfect solution. But perfect didn't mean practical. The swamp hauler, as it came to be known among engineers, required specialized fuel. Its imported powertrain couldn't tolerate the lower-grade diesel common in Siberia. Maintenance intervals were short, parts were expensive, and no local technicians could service the high-pressure filtration system without factory support. When the first cold snap hit, -45°C, the digital systems failed. One test unit reportedly short-circuited after condensation froze inside its sensor hub. The cost of the prototype alone exceeded the budget for 5 standard Kirovets units. And while the machine did float, it couldn't climb frozen inclines without damaging the track bed underneath. Eventually, the project was shelved, not because it failed, but because the infrastructure around it did. There were no heated shelters to store it, no transport platforms are wide enough to carry it across regions, and no satellite support to run its guidance system once it leaves the testing corridor. One prototype may have been converted for geological work near the Yamal Peninsula, but even that remains unconfirmed. Today, the K9000 Swamp Hauler doesn't appear on spec sheets or company records. Only a few trade show slides and a photograph taken from a distance of 300 meters remain, a tractor that did everything it was designed to do, except justify itself. Ranked 4th, Massey Ferguson twin engine puller. The crowd didn't care what it harvested. They only cared how loud it got. In the late 1970s, Massey Ferguson unveiled something that had no place in a field, no role on a farm, and no commercial purpose whatsoever. A twin-engine pulling tractor built not for crops, but for crowds. Mounted on a reinforced steel chassis, the prototype carried 2 massive V8 diesel engines. often Detroit 8x92s or Perkins blocks, coupled through a synchronized crankshaft system into a single rear transmission. It had no PTO, no hitch, no cab comfort, no emissions gear, just noise, torque, and the ability to rip a sledge across a stadium floor in under 15 seconds. This machine wasn't for sale. It wasn't even listed in dealer catalogs. It existed purely as a statement, a mechanical branding exercise meant to show that Massey Ferguson could compete not just in yields, but in raw mechanical power. The prototype first appeared at regional pulling events in North America, sometimes painted in standard Massey red, other times stripped of logos entirely. Observers recall its sheer physicality: black smoke pouring straight into the stands, twin exhausts vibrating in sync, the front end lifting inches off the dirt before the weight box dropped and forced it back down. No electronic control units, no telemetry. The only data came from the roar of the crowd when the run was clean. For Massey Ferguson, the puller wasn't just a machine, it was a recruitment tool. Dealerships would showcase photos of the twin-engine build on showroom walls. Field day booths printed posters. Farmers brought their kids to hear it start. In the background of every serious agricultural decision, there was this mechanical monster reminding buyers that their tractors came from a company that understood performance. But as regulations tightened and competition modernized, the puller quietly disappeared. It had no place in an industry shifting toward fuel efficiency, GPS automation, and emissions control. It couldn't be shipped overseas without customs classification issues. Insurance companies refused to cover it, and once AGCO acquired Massey Ferguson, the program came to an end entirely. One of the original units was disassembled. Another survives, barely, in a private shed, restored for static display, its twin engines now locked in place with rusted belts and caution tape. No other mainstream manufacturer attempted a twin-engine show tractor again, not because they couldn't, but because the era had passed. It was built for a time when horsepower was a spectacle, and noise was the message. Ranked third, Fiatagri Volcano crawler. Most tractors are designed to withstand high temperatures. This one was built to survive it. Sometime in the mid-1980s, Fiatagri engineers in Italy constructed a prototype crawler for one specific environment, the volcanic slopes of southern Europe. Nicknamed the Volcano, the machine was a low-profile, high-traction crawler tractor designed to operate in ash-heavy soil, steep basalt terrain, and intermittent exposure to sulfur-rich gas. It wasn't designed for speed. It wasn't designed for comfort. It was engineered for survival, not of the operator, but of the machine itself. The crawler was powered by a standard Fiat 8000 series diesel engine, rated between 100 and 120 horsepower, but almost everything surrounding it was customized. The engine was sealed in ceramic heat shielding. The air intake was routed through a dual-layer filtration stack capable of removing microparticulates down to the size of volcanic glass. The exhaust system was fully enclosed, vented upward through a fluted aluminum alloy stack with directional shielding. Cooling was closed-loop. There was no open radiator to clog with ash, and the chassis was weighted for stability on high-grade inclines where tipping wasn't just a risk, it was inevitable. The Volcano wasn't a marketing stunt. It was developed as part of a regional agricultural initiative aimed at utilizing marginal lands on the slopes of Mount Etna and other dormant volcanoes in Sicily. The goal was simple: to make viticulture and olive farming viable on terrain that was too unstable, too steep, or too hot for conventional equipment. The crawler passed early tests. It ran for hours in ash-laden conditions. It navigated tight terraces. It kept its filters clean, its drivetrain calm, and its operator alive. But it cost more to build than any conventional Fiatagri tractor. The ceramic shielding cracked after thermal cycling. The replacement air filters were too expensive for small producers. The cooling system failed due to temperature swings common in high-altitude valleys. And the logistics of transporting the crawler between isolated farms made it economically unfeasible. No production order followed. Only 2 prototypes were reportedly built. One was dismantled after testing. The other, stripped of its internals, was spotted rusting behind an orchard in the southern Sicily. its ceramic armor long since shattered. Fiatagri never issued a press release. The project was never officially canceled. It simply stopped being mentioned. Today, no technical drawing of the Volcano survives in public archives. Its only remaining description comes from a trade journal footnote published in 1987, which referred to it as a field unit designed for operation under extreme thermal particulate stress. A machine too specialized to scale, too expensive to replicate, and too far ahead of what the land and the market could support. Ranked second, Big Bud 950 experimental build. There is no photograph, no video, no record of it running, and yet everyone near Havre, Montana, knew what it was. Sometime after the last appearances of the Big Bud 165-747, the largest farm tractor ever built, rumors began circulating that big equipment was working on something even bigger. A 950 horsepower, ultra-wide, steel-frame monster designed not for fields, but for open land measured in miles. Some said it would run on twin Caterpillar 3412 V12S. Others claimed it was a turbocharged derivative of the 16V149. Most agreed it was never fully assembled. The project was never announced. No serial number was issued. But somewhere behind the main fabrication building, engineers quietly began welding a chassis that was longer, heavier, and more aggressively reinforced than anything the company had ever put on wheels. It wasn't built for the market. It was built to see how far the concept could go. A test bed for load stress, cooling volume, axle dispersion, and soil displacement at scale. In theory, it would have pushed close to 950 horsepower and carried enough torque to till uninterrupted swaths of virgin soil at 8 meters wide. But the timing was wrong. By the late 1990s, the economics of farming had undergone significant shifts. No customer wanted to buy a machine that couldn't legally travel on highways without escort permits. The frame exceeded 6 meters in transport width. Tire sets alone cost more than the average mid-sized tractor. No supplier would commit to support, and fewer farms were being consolidated into the mega-acre spreads that justified such machines in the first place. Even internally, there were doubts. Engineers couldn't solve heat rejection at that power class without fundamentally redesigning the cooling system. There was no off-the-shelf transmission capable of handling both torque loads without custom casting, so the project was paused. The chassis was moved out back. The idea was shelved. At least one partial build remained visible for years behind the Havre shop, slowly rusting, frame intact but unpowered. In first place, Oshkosh-Massey defense tractor. No such vehicle appears in any NATO field manual. No known inventory record lists it under agricultural, engineering, or transport support. Yet across 3 decades of declassified logistics memos and oral testimony from defense contractors in both the United States and Canada, a pattern emerges. One that points to a joint experimental platform built not to fight wars, but to operate immediately after them. The Oshkosh-Massey defense tractor was never designed for civilians. It was not an adaptation of any commercial model, but rather a tactical hybrid that combined Oshkosh's military-grade 8x8 mobility platform with modified Massey Ferguson agricultural control systems. The result was a field-deployable tractor capable of being airdropped, armored, sealed, and operated within 72 hours of terrain clearance. In zones classified as degraded, denied, or contaminated, its function was not offensive, nor was it conventional. The vehicle was designed to pull heavy implements, including grain drills, sterilization tanks, irrigation kits, and fuel sledges. Any tool that could restore minimal agricultural functionality to a reclaimed zone or forward operating region. Early design notes reference NBC-resistant filters, fully enclosed cabs, redundant power electronics, and a diesel engine tuned for long, idle durations with minimal maintenance. The tires were wide enough for soft soil, narrow enough for transport crates, and durable enough to survive airdrop impact with modular skid buffering. Payload tolerance matched light armored vehicles. Everything about the machine was optimized for one scenario: the reintroduction of food systems in the wake of limited infrastructure failure, including the aftermath of a nuclear event. No press release ever mentioned the program. Procurement was classified under non-combat engineering. One engineer recalled conducting field tests at Cold Lake, Alberta, at dawn under a no-fly observation status. The tractor reportedly performed its mission, completed terrain pulls in sub-zero ash-rich conditions, and was airlifted back before midday. But the project ended before formalization. As the Cold War dissolved, so did the strategic justification for deployable agricultural assets. Logistics chains were consolidated. Global doctrine shifted. Funding retracted. The few components that were built, mostly frames, filtration modules, and a partial control pod, were either redistributed to other programs or quietly disposed of. No chassis remains in the public record. No photographs exist that can be verified as authentic. Only a line item from a Canadian defense budget in 1988 references a ground-rated agro-logistics vehicle, joint-funded, status, terminated. Today there is no museum exhibit on display, no contractor brochure, no technical dossier stamped with its name. The Oshkosh-Massey defense tractor was never declared operational and may never have been fully assembled. But its concept, its frame geometry, and its doctrinal purpose point to one conclusion. Someone, somewhere, planned for a war to end and for a field to be plowed immediately after. There are no model numbers to search, no parts to order, no resale listings because these machines were never released. Not because they failed, but because the world around them changed faster than they could. Regulations shifted, fuel costs rose, farms consolidated or vanished, and the machines built to solve impossible problems were left in pieces, stored under tarps or cut back to scrap. What remains isn't documentation, it's absence. And in that absence, we see the outer edge of what agricultural engineering once tried and what it quietly walked away from.